Okay, can you hear me?
You need to use the microphone on stand, I think.
I have to use that one? So this one's on, I guess. Oh, okay, too bad. So I can't run around. Okay, let's do it this way then. If I would want to summarize my work very briefly, it would be that I formally proved that cardinality is safe. And if you happen to believe in proof irrelevance, I guess you can go for coffee now. If you're still here, then you probably want to know something, and I guess that falls into one or more of these four categories. You might want to know what exactly is cardinality and what do I mean by safe. Then you might want to know why I think this is true. Having heard about the proof, you might wonder whether I really am sure about the proof and why do I think this is edited correctly. And or you might be one of those who ask questions who are not really questions, and they tend to start with but. So let's address these in order. So what is cardinality? First and foremost, it's a analysis and transformation. It's trying to change the definition of functions to take more arguments. So it's trying to eta expand them. The motivation is that it allows you for faster function calls. So the generated code will be faster. In this instance, it's a forward arity analysis. So it looks at how things are being used. And you can see on the left that the factorial function is defined taking one argument, but it's always called passing two arguments. And then the cardinality analysis concludes that it's okay to eta expand it to two arguments. So far, this is not very new. This is you can find it, for example, in Gill's thesis from 19 years ago. So you might wonder why hasn't THC been doing that for 2 decades now? And the reason is there's a catch, and that's in lazy languages with thunks. You can think of a thunk as a function with 0 arguments, so it makes perfect sense to apply the same transformation there and add more arguments if that fits the bill. But you would transform a thunk into a function, and it would no longer be shared. And if you lose sharing, then you might be repeating the work, and the program goes slower. So that's something you don't want the compiler to do. Unless, of course, it's okay to do it. And when is it okay to do it? It's okay to do it if the thunk is being used at most once anyway, and there's no point in sharing the result, because not going to be used. And that's why a good arity analysis needs the help of a precise cardinality analysis. So a cardinality analysis tells the compiler, this thing is being used at most once. And with that information, you can do more. And in the cases where I wanted to apply the transformation, I needed a cardinality analysis that's precise even in the presence of recursion. So even if something's being called from within a recursive function, if it's being called at most once, I'd like to know about it. So I came up with a new cardinality analysis based on the notion of co-call graphs, which gives you a bit more information than just called at most once. So here are 2 simple examples. In the first, we know that P and X and Y are being called at most once. But you also know that while P and X can be called together, or P and Y can be called together in one execution of the expression, there's no case that X and Y are going to be called together. And this is an important bit of information. We would not have that in the second case, where we don't know what F is doing. So it's quite likely that X and Y are going to be called by F. It's also quite likely that X is being called multiple times. So we have the self loop, but we still know that F is being called at most once. So this is where the precision comes from. And yeah, that's in a short summary. Cardinality, it's a forward arity analysis with co-call cardinality analysis. It's in GHC, released on my birthday, 7/10, enabled by default. And the motivation was that this way we can actually let left folds take part in list fusion and still get good code. So this was the original motivation for the whole work. Now it's a transformation that's enabled by default. So whenever you compile a Haskell program, my code messes with it. So I would not want it to make it worse. So this was my worry. And of course I wrote a few test cases and I observed no-flip numbers, and it did not make things worse, but our test suite is not very complete. So I wanted to have something better. I wanted to prove that it's always safe for the compiler to apply this transformation. And this is what I mean by safety. It's nothing will get worse by applying it. Hopefully it will get better, but not worse. So this is that's what I mean by safe. It also implies functional correctness, but I'm mostly concerned about the operational property of not making things worse. It's also the same notion as improvement, if you know the work of Sands, but that would make the title even longer, so I prefer safety. How can call arity not be safe? So what could possibly go wrong? If there's a bug in the analysis, then it would do too much. It would eta expand more than it should. And as we've seen, if we eta expand more, then we lose sharing. If we lose sharing, we duplicate work. And any such work that we duplicate, in general, will be something that's allocating something. So it will be allocating code. Therefore, we will observe that the number of allocations is increasing. And that's my approach to proving safety here. I prove that the transformed program does not allocate more than the original one. So by this line of reasoning, I know that there's no bug. At least no bug of that kind. So how did I go about this? The first ingredient for the proof is you need to have a semantics that's precise enough to capture allocations. So the usual denotational standard semantics don't work. Launchburrow's natural semantics for lazy evaluation is a natural choice here because you have explicit heaps in the judgments, and you can just look at the size of the heap, and that's the number you want. It turned out during the proof that I'd rather prefer to work with a small step semantic, so I reached out to SetStuff Mark I virtual machine, which is in a sense just the small step variant of Launchburrow. So they are equivalent, and it works well together. The second ingredient in the proof that's worth mentioning is I needed a more abstract and a bit more detailed and also nicer to work with data type for the results of a cardinality analysis. So just at most once or not is not enough information to go through the proof, and also co-call graphs are not good enough. So I came up with trace trees without claiming any novelty here. I'm sure that's quite a natural concept, which describe the future calls performed by an expression as a possibly infinite tree. So in our two examples, in the first one we see that evaluating this expression will call P and then either X or Y, whereas in the other case, after the call to F, we can expect any number of calls to X and Y in any order. And this is a somewhat nice data type to work with in the proof. And then for those who like for those who like partial orders and fancy math, it's a Galois immersion of co-call graphs into trace trees. And the third ingredient to getting this proof done, because it would be a rather large thing, I guess, I broke it down into smaller steps and performed a refinement proof. So on the very left, the proof is that a Arity analysis is safe if a cardinality analysis is correct, and I don't make any assumption about how the cardinality analysis is implemented, so it's completely abstract in that. And then I refined that to one that produces trace trees, which is still an abstract concept, so it's not something you would implement. The next refinement step would then show that the same holds for a analysis returning co-call graphs as long as they approximate the corresponding trace trees in the abstract result. And finally, I showed that call arity as implemented is an instance of this specification. And the idea is that this allows me to maybe change the implementation a little bit and not have to redo all the proof, but only the proofs further on the right. And it might also be something that could be reused to prove similar results for a completely different cardinality analysis by just using the left bits of the refinement proof chain. So maybe this gives a hint that the proof is not completely trivial. So you might wonder whether the proof is correct, and I would do the same, especially if I know that I've written it. If I had written it on paper, that's why I don't like to write proofs on paper, but rather do it machine checked. So all this was done in Isabelle to implement the syntax, the semantics, the data types, including fancy infinite trees, which is fun. And then, of course, the actual proof. And at the end, I know that the theorem that I had on the slide earlier, this is how it looks in Isabelle, is correct. And I don't have to bother any reviewers with checking my proofs, which is probably good for the reviewers as well. Right. So there's a but. So every time we do some formal model of something, some proofs, whether it's machine checked or not, then we have on the one side the real world with like fine details and little things, and on the other side we have our formal model, and they don't look precisely the same. There's not even an overlap. There's a gap in between, and that's the formalization gap. And I think it's always good to discuss the formalization gap frankly and very explicitly in any formalization. So if I try to do it in paper, there's this whole section on these things, and I do a little bit here. For example, the analysis works on THG core, which is a typed language, and the typeness of it is an important feature, people say. Yet my formalization doesn't include any types. It's an untyped lambda calculus, and so there's a gap. But then I argue that because the core Arity analysis doesn't make use of the types and looks through them completely, it's fine to have this as a formal model. And using such meta-arguments, the goal is to bridge the gap. But I guess in most cases we will, despite our best efforts in making meta-arguments, we'll never bridge the gap completely. There will always be a little hole left. And then the question is the hole large enough to fall into? And maybe unfortunately, in this case it was. And I'd like to describe the bug that was still there, despite all the formalization work that went into it, because I think it's a nice example. And this bug was reported by Neil Mitchell, who found that the test suite of his shake library was performing very strangely, starting from GHC 710 release candidate 3, so we were almost ready to release, and then suddenly the bug appeared. And then we looked at it and we boiled it down to this is the boiled down version of what has happened, and I'd like to walk you through it. So the library had a function, let's call it foo, which immediately calls error. And the function would take an argument which it doesn't use. So the first thing that happened is that the strictness analyzer comes along and looks at the function definition and finds out that once you pass one argument to the function, it's going to bottom out immediately. So it's either going to be diverging or in this case throwing an exception. And it staples this information onto the function definition for later use. Next thing that's happening is that cardinality comes along, and it turns out that all calls to foo pass two arguments. So as described earlier, that's what cardinality does. It detects this and it explains foo to take another argument. So we have the third code. And then finally the simplifier comes along and has a look at this case expression, and it notices there's no point in passing two arguments to foo if it's going to be diverging anyway after taking the first argument, and that's what the strictness signature says. So I'm going to remove the second argument from the call, and because it's diverging, there's no point in having case alternatives anymore, so I'll remove all of them and have an empty case, which is something you can have at core. But obviously the resulting code is completely bogus, because foo A does not diverge. In fact, it's still a value and quite immediate so it'll just return directly, but there's nothing to return to anymore. And the interesting thing is it didn't crash the compiler, it didn't even crash the program. It would rather, instead of raising the exception, continue execution at some random point nearby in the program code, yielding quite interesting behavior. So we fixed it for 710. The fix was that cardinality would simply not eta expand beyond the number of arguments that occur in such a strictness signature if it's there. The safety proof still holds for the modified program because the safety proof only requires the code to do not too much eta expansion, so it's always okay to do less. It's always safe to eta expand less. But the formalization gap is still there. I don't have a formal model of all of GHC's annotations or what the simplifier does. And maybe this is yeah, maybe there's a problem of trying to formalize something within a system like GHC, which is large and has grown and was not made for formalization in the first place. Yeah, I hope you have any questions. So what's the conclusion? There hasn't been many attempts to formally prove that something is an optimization, and even fewer that have done so in a machine-checked way. So yes, we can. That's the main result, I guess. There are benefits of doing it. Just like in the previous talk, if you formalize something, you find a bug. I also found a bug in the implementation, or rather in the algorithm, that was missed by my test cases. So it did improve the quality of the code. The big advantage of having a machine-checked formalization is that it's much easier to change and to refactor. So if I change the code and I have a many-page paper proof, then I would have to go through all the proof and look at each bit carefully and see what has to change. Whereas with a machine-checked model, I will just change the definitions and then it will tell me where my proofs go wrong and I can fix it. It's like refactoring in Haskell. It's much more pleasant than refactoring pseudocode on paper, I guess. And of course, doing it in a theorem prover gives me much higher assurance that the proof itself is correct. And my personal opinion is that I would hope that the tools become good enough so that in some future it's completely normal that all your proofs that you submit to something are also machine checked, just the way that today if you propose an algorithm, you are expected to have implemented it, at least as a prototype. And if you just talk about an algorithm that's super cool, but you don't have any code, then people will at least ask questions. But we're not quite there yet. Doing this in Isabelle had turned out to be quite an undertaking, quite a lot of work, some of it tedious, and that I wouldn't have had to spend if I just did a pen and paper proof. And then, at least in this case, we find that the formalization gap still remains. I have a proof of safety and of functional correctness as well, and yet it changed the semantics of the program. Because, of course, I could not formalize all of GHC. I guess I can start with questions earlier.
In the bug that you showed us, you noted that your technique detects bottoming out, and you said in this case an exception. Can you detect other forms of divergence?
I didn't detect the diversion. That's the strictness analyzer in GHC.
Oh, okay.
So it's already there. I'm just making sure that I don't do anything stupid if the strictness analyzer has already found out something about the code.
Thank you.
So a related question. I like the work, and I'm very sympathetic to the difficulties in the formalization gap. But when you showed us Neil Mitchell's bug, my first reaction was not to think that you needed to know all about what's happening inside GHC, but rather that you started out with a safety property that's 2 weeks. So it's indeed true, or looks true, that the buggy code does not allocate more than what you started with, but has very different divergence properties. So would it be reasonable to go back and say, oh, well, I want my safety theorem to say not only does call Arity not increase the number of allocations, but also call Arity does not change the property of whether forcing a term diverges. And I just don't know whether that's a reasonable thing to ask for.
I guess I didn't make that clear. I also have a proof of functional correctness within the system, so the semantics are unmodified, and that includes, I guess, termination properties. But the semantics doesn't cover the effects of the simplifier. So the safety proof is not the one that went wrong, but rather the much more simpler functional correctness proof, which is there, of course, I guess, as well.
Okay, thanks.
Oh, looks like I have still 5 minutes to talk about stuff I went to. So if you like swing dancing, this evening in Vancouver there's a swing dancing social event that I'd like to attend. I'll go there around 8, Lindy Hop. If you want to join, talk to me. That's fun.